All right, so let's do a quick example of this. All right, if we have 209 joules of heat is required to increase the temperature of 50 grams of water by 1 Kelvin. What is the specific heat for water? So we're going to take the Q equals mc delta T, and we're going to rearrange it here to where I have Q over m times delta T. And here, we're told the amount of heat, we're told the mass, we're told the change in temperature. We need to find C. So here, we're going to have 209 joules of heat. Now, in these heat capacity problems, units are really important. You got to make sure you're watching whether you have joules or kilojoules, whether you have mass or moles, and what your units of temperature are. So really be diligent in keeping those units in your calculations here. If I have 50 grams is the mass of water I'm dealing with, and the change in temperature is 1 Kelvin. And so it's going to be a positive value here. We go in and we'll see that the specific heat for water, C for H2O, is 4.18 joules, that's on the top, per gram times Kelvin. Or again, sometimes you'll see degrees C down here. It doesn't matter. It's the same magnitude of a unit here. So this 4.18 number, you're going to be seeing a number of times, and so you're going to commit that to memory as well. So here's one thing you need to know. All right, the greater the heat capacity of a body, the more heat is required to produce a given rise in temperature. So think of heat capacity like a thermal inertia. If something has a high value for heat capacity, something like water, so water has a relatively high number, whereas many of your metals, right, a lot of times your heat capacities for metal are something like 0.5, right, and it's going to vary. So if I'm comparing something like a metal that has a heat capacity of 0.5 joules per gram degree C or Kelvin, that means that the metal has a smaller capacity to hold on to heat before it has to transfer it. So if you think about a piece of metal or a hot pan, you put it on the stove, you turn the heat on, metal pans will heat up pretty quickly. Right? And that's because they don't have a lot of capacity to hold that heat. So you heat them up and they're gonna get hot pretty quickly. By the same token, you turn the heat off, right? So let's say you were gonna go fry an egg and you turn the heat on and then you change your mind, oh no, I want oatmeal instead. So you turn the heat off. That metal pan, because it's got a low heat capacity, is going to also lose that heat very quickly as well. Now compare that to water. It takes a long time for water to heat up. Water has a high heat capacity, and so it's got a low thermal inertia. So you start heating water, it takes forever to heat up water. And once you got it to boiling, you turn the heat off, that water is also going to stay warm for a long period of time. It can hold on to its heat pretty well. So in general, the greater the heat capacity of a body, the more heat that is required to produce a given rise in temperature. It doesn't take as much heat to change the temperature of metal. It takes a lot more to raise the temperature of water. All right, now what about phase changes, right? So we have the equation to do temperature changes, Q equals mc delta T. Well, for phase changes, the formula looks like this. You have the delta H of phase change, right? And so we could be talking about fusion or melting, or the delta H of vaporization or sublimation, whatever that phase change is, there's a delta H value, equals Q, heat, over the amount. And then amount can either be in terms of moles or it can be in terms of the mass. You'll see these terms given both ways, but you're going to have Q on top and the amount on the bottom. For water, if you look up the values, the delta H of fusion for water is 6.01 kilojoules per mole. The delta H of vaporization is going to be 40.67 kilojoules per mole. Right, so it takes a lot more energy to vaporize water than it does to melt it. So if I'm going from the liquid to the gas phase, I've got to overcome all those hydrogen bonds. There's a lot more energy involved here. Now, in terms of the signs, this is where you've also got to be careful. The magnitude of the number stays the same. The sign is going to be determined depending on which direction you're going. If energy is put into the phase change, so if I'm trying to melt ice and I'm going from a solid to a liquid, we know we got to put energy into the system in order to get that to melt. So this value up here would be positive 6.01. If I'm talking about liquid freezing into ice, well, this value will be negative. I need to remove 6.01 kilojoules of heat for every mole of liquid water I'm trying to freeze into ice. And the same thing would be said for vaporization, right? If energy is released in the phase change, so if I'm going from a vapor to a liquid to a solid, then this value is going to be negative. Usually this number is reported in textbooks and tables as being positive. So you'll have this number as a positive in your problem, but you always have to be thinking, all right, is the heat coming or going, and do I need to put a negative sign out front? Right? So we always got to keep an eye on that. All right, so let's put these two problems to work here, these two equations to work. We're going to go back to our heating curve here. And this is what a typical heating curve problem is going to look like. It's going to say how much total heat is required to convert 1 mole of ice that's initially at minus 25 degrees C to water vapor at 125 degrees C, all under constant pressure, right? So you're always going to see that little clause thrown at the end. Pressure does, we don't calculate pressure. We just realize, all right, I've got to keep the pressure constant throughout all of this. And then you're going to be given some values, right? So these are not numbers you will memorize. They're either going to be given in the problem or they're going to be given in a table in the chapter. So you're going to have to use this information to solve the problem. Basically, for each of these little segments, is we're going to calculate what is the enthalpy change for each of the segments, and then we're going to add them all up. So this plus this plus this plus this. So we're going to get 5 numbers in this problem in order to figure this out. We just need to determine which segment is a temperature change, and we use Q equals MC delta T, and which are we dealing with phase changes. And so we have to use one of these. So let's start with the segment A to B. We're going to do the first two, and then I'm going to pause this and let you guys work on the last bit of segments, and then we're going to add it all up together. All right, so looking from A to B, right, so at A, we have minus 25 degrees C ice. And as we add the first bit of heat, that's going to go into changing the temperature of the ice from minus 25 degrees C up here to 0 degrees C ice. So we have to determine, is this a temperature change or a phase change? And it's going to be a temp change. So we write Q equals MC delta T. And we want to figure out what the Q or the enthalpy is. So we start with the mass. All right. Now here, all right, notice that all of my specific heats are in values of grams. The problem told me moles. So I'm going to need to convert from moles of ice, H2O, to grams. Well, that's easy. I can just use the molar mass. And so I know I'm dealing with a sample that is 18 grams of H2O. So I have 18 grams of ice to start with. So that's my mass unit. And then I need to use the specific heat that is appropriate for this phase. So since I'm dealing with ice, we're going to start with 2.09 joules per gram Kelvin as my specific heat here. All right, so I don't want to use the one for water because I don't have water, I have ice. Now my temperature change, delta T, is going to be T final minus T initial. The final temperature here is 0 degrees minus negative 25 degrees C. So my change in temperature is a positive 25 degrees. Now, my units of specific heat are in Kelvin. The problem is in degrees C. It doesn't matter because I'm talking about a change. So I can easily just convert that to Kelvin to make my units work. We're going to take 18 times 2.09 times 25. And the Q here is going to be a positive 940 joules of heat. So grams and grams cancel, Kelvin and Kelvin cancel. I'm left with joules. All right, so that is segment number 1. And then we just move on to the next segment. All right, so segment B to C. Notice I'm adding heat here, but the temperature is not changing. I have a flat line going up here. So that's going to tell me that I have a phase change. This is going to be going from ice to water, but the temperature is at 0 degrees C. Change the color up here. So we look at segment B to C is a phase change. All right, so the phase change I'm looking at is going to be fusion. All right, the delta H of fusion, right, is 6.01 kilojoules of heat is required for every 1 mole of the substance we're dealing with. In this case, we're dealing with water. Okay. Well, I'm trying to find out the specific amount of heat we're dealing with. So I'm trying to find the Q, and I know I have 1 mole of H2O. So here is my enthalpy of phase change, and I'm trying to solve specifically for this Q. Now this problem is nice because it's already at 1 mole. So I know that for every mole, it's going to take 6 kilojoules. And so I don't really need to do any calculations here. And so the Q for this segment is going to be a positive 6.01 kilojoules of heat. I have to put that heat in to go from ice to water. Now, you probably have noticed this already, but they give you units of kilojoules, and we've already started working in joules. Just make note of that. We're going to have to choose one or the other to report our final answer at the end. All right, so we've done segments A to B and B to C. What I want you guys to do is I want you to calculate the heat involved in segments C to D, D to E, and E to F. So you have to figure out for each of these 3, are you dealing with a temperature change or a phase change? Use the right equation, get the value of the energy, and then we're going to add them all up. All right, so I'm going to pause the microphone. I'm going to give you guys just a few minutes, and then we'll come back and we'll see that we all got the same answer. All right, so go ahead and do that. All right, so let's look at our segments here. So segment C to D, we have a temperature change. Right, so I notice that I'm going from left to right, so I'm adding heat, but I'm also going up on the y-axis. So we're going to use Q equals mc delta T. The mass of the H2O is still 18 grams. I'm dealing with water, so I need to use this particular specific heat, 4.18 joules per gram Kelvin. And to go from 0 degrees C up to 100 degrees C, that's a change of 100 degrees. Again, a degree C and a Kelvin are the same. And so we're going to get something like 7,520 joules of heat given off, or put into the system, so it's positive. All right, from D to E, we have a phase change. The temperature is not changing, but I'm going from the liquid phase to the vapor phase. So I use the delta H of vaporization. That's 40.67 kilojoules per mole. Since I'm dealing with 1 mole, the Q value is just going to be the same. It's 40.67 kilojoules of heat must be put in order to get us to the vapor phase. And then finally, the last segment, going from E to F, there's a temperature change again. Q equals mc delta T. 18 grams, 1.84 is my value for C. And we're going to go from 100 degrees C up to 125. That was stated in the original problem. So I have a change of 25 Kelvin. And that's going to give us somewhere around 830 joules. To do the total enthalpy, H total, we're going to take all the values so far, and we're going to pick, let's just do kilojoules. All right, so we had 0.94 kilojoules for the first segment, plus 6.01 kilojoules for the second one, plus 7.52 kilojoules for C to D, plus 40.7 kilojoules for the D to E. And then finally, we had 0.83 kilojoules for the last segment. So we're just going to take and sum all of those up, and our delta H total is going to be 56 kilojoules of heat. Now, we always check, is like, all right, is that amount of heat being added or is it released? And since we're going from solid up to the gas phase, I got to put heat in this entire time. So my value here is positive. Right now, so if we can change this problem up by giving you a different substance. And so these values would have to change. The boiling point and melting points would change. They could give you fewer segments, but in general, you just need to kind of sketch out a heating curve, figure out which segment is which, and then just use the right equation to do that. But generally, they are pretty straightforward problems in that way. Right, and that's it. All right, any questions on heating curves and calorimetry? And we have two equations you need to keep track of. Right. With the negative sign only affect the value at the end. All right. So here's the thing. So in these heating curve problems, if we're going from, say, solid to a gas, all of your additions of heat are going to be positive. But you could turn the problem around another way and say, okay, if I start with steam and I want to now get it down to ice, each of those segments we have to remove heat. So all the segments you would have a negative value for your Q, right? And so just looking at, say, the temperature change, your mass value is always going to be positive. Your value for specific heat is always going to be positive, but where the negative would happen would be in the temperature change, right? So if you're dropping in temperature, you'd have a negative here, and so your heat given off is going to be positive. We didn't have that in any of these because we were going from, bottom left, we were going up in terms of heat. But if we turn the problem around, the temperature change is what's going to make that value negative. I always look at the end of the problem and make sure that I had my signs right. So again, even if you're playing fast and loose with signs, just double check your number at the end and say, hey, is this heat coming or going? The number is going to be the same, but you just need to check for the signs. All right, now we're going to change gears a little bit, and let's do a couple of other enthalpy type problems. The first one has to do with burning things in a calorimeter. So let's do a couple of those. All right, so it says we had a 0.5865 gram sample of lactic acid, and we have the formula given. It's going to be burned in a calorimeter whose heat capacity is 4.812 kilojoules per degree C. All right, the temperature is going to increase from 23 up to 24. So what is the delta H of combustion for lactic acid per gram and per mole? All right, so in essence what we're going to do is we have a device here, this calorimeter, that's going to keep the pressure constant. We know how much heat is going to be absorbed by the calorimeter per degree C. And we want to see, how much heat is going to be involved per gram and per mole. Now, with our temperature change equations, right, so we talked about Q equals MC delta T, but we also discussed Q equals big C delta T. Right? Calorimeters have got heat capacities, not specific heat capacities, but big C values. And so even though there's a mass involved with the lactic acid, we're not using that in the first step. We're going to use the calorimeter constant first, and then we're going to come back and figure out how much heat is used per gram and per mole. So the first thing we have to do is figure out the raw heat involved. So Q is going to equal, right, we start with the calorimeter constant, 4.812 kilojoules per degree C. Make sure you put your units in, and it kind of triggers you to either use joules or kilojoules in your calculation. All right, our change in temperature, we do the final temperature, which is 24.95, minus the initial temperature, 23.10 degrees C. All right, that's going to be a positive temperature change, meaning energy is going to be absorbed by the calorimeter and given off by the combustion of the lactic acid. So when we figure out what Q is going to be 8.90 kilojoules of heat. This is going to be heat absorbed by the calorimeter. So that's a positive number. But we're looking at the delta H of combustion for lactic acid. The lactic acid is giving off 8.9 kilojoules of heat given off. And so we want to make sure we're dealing with a negative number here. Now, that's a raw heat value. We have kilojoules. We want to figure out what is the delta H of combustion per gram and per mole. Knowing that it is an extensive property, the more of it we have, the more heat we're going to get. But we want to do this in terms of grams. So the delta H of combustion, we're going to take the negative 8.9 kilojoules and divide it by the mass that we actually combusted. So 0.5865 grams. And so this is going to be negative 15.2 kilojoules per gram. Right? So that's one of the numbers. It also wanted it per mole. So I can take the negative 15.2 kilojoules per gram, and if I want to convert to moles, grams is on the bottom, so I need to have grams on the top, moles on the bottom. I calculate the molar mass. In 1 mole, there is 90 grams of lactic acid. So this is going to be negative 1,368 kilojoules per mole. And so these are the two values that I'm going to report here. So again, it's dependent on the sample size. So the raw heat dependent on this number, but these two, when you see delta H's of combustion or vaporization, they're usually done on a per mole or per mass amount. All right, let's try another one. All right, we got 1.8 grams of octane, and that's going to be burned in a calorimeter, who's got a calorimeter constant of 11.66 kilojoules per degree C. The temperature is going to increase from 21.36 to 28.78 degrees C. What is the delta H of combustion for octane per gram and per mole? All right, so what I'm going to suggest you do is pause the video and go ahead and try to solve the problem. And then once you have it, hit the play button again and we'll see how you did. All right, just like the last problem, Q is going to equal to big C times delta T. So the heat involved, we're going to take the calorimeter constant, 11.66 kilojoules per degree C. That's our calorimeter constant. Our temperature change, the final temperature is going to rise to 28.78 degrees C minus 21.36 degrees C. That's a temperature change of 7.42 degrees. And so the Q is going to be 86.5 kilojoules of heat absorbed by the calorimeter. And so when we're trying to figure out what's the delta H of combustion, the opposite sign is what's given off. So negative 86.5 kilojoules is given off. Now, how much is that going to be per gram? So we divide it by the sample size. 1.8 grams of octane goes on the bottom. And so this is going to be negative 48.1 kilojoules per gram. All right, to get it per mole, we can take our gram value. All right, so the kilojoules we want to keep in the numerator, we want to change the denominator. So grams is going to go on top, moles is going to be on the bottom. 1 mole of octane has a mass of 114.2. And so this is going to be negative 5.5 times 10 to the third kilojoules per mole. And so that's the heat of combustion that we would report, both in per gram and mole here.